Well, good evening, everyone, and welcome to the Brian Crombie Radio Hour on Saga 960. I had a gentleman on just a little while ago talking about ventilation systems, and he recommended I should speak to the expert that he thought was in the business, and a gentleman who's a professor at the University of Guelph by the name of Dr. Stephen Newmaster. And he is joined together to start a company by the name of Songbird Life Sciences. Dr. Newmaster is a genomics professor at the University of Guelph. He specializes in molecular diagnostic systems of plants, probiotics, and pathogens. He's a leading scientist in the development and validation of mobile detection systems for species identification, DNA barcoding, and nuclear magnetic resonance chemometric systems for the identification of natural products. And he's currently working with a team of scientists on a point-of-care diagnostic tool for pathogens, which would include bacteria, viruses, and also COVID-19. So, Doctor, hello, Professor. How are you? Welcome to our show.
Thank you, Brian. It's good to be here, and it's good to share knowledge.
We appreciate it. So tell us about a little bit about your background and how you came to be interested in point-of-care testing.
Yeah, sure. So as you've already said, I'm a genetics professor at Guelph for 25 years, and my background is in molecular diagnostics. So we sequence and build databases to be able to identify life, identify different things, including viruses. And we take that data and we democratize molecular biology by bringing it into the hands of users that need it in mobile situations. I've done this for US military in war zones where we're looking at warborne pathogens detection. So I've worked on this out of Silicon Valley in California to build these gadgets. They're called, they're flow diagnostics. So they're very small, one button you push, you put in a sample and you get a readout on a laptop or some kind of small device that's connected to it. We do this for the food industry, and we've been doing this for over 10 years, including pathogens that keep your food safe. So keeping Listeria out of food or E. coli. And now we've been called in to work on pathogens that are affecting the human population. Yeah.
And Songbird is what?
So Songbird is a business that commercialized some of this technology this past spring. So it's really, it's a Canadian business. It's a business that was just started up, and it's a business that assesses space, the risk of a pathogen in a space and to infect people. So we look at environmental detection on surfaces, in the air, in the water, and then in humans. And the latest innovation that we've had is having a point-of-care device for humans that's been approved by Health Canada.
And this point-of-care device, can you describe it for us?
Yeah, it's small. It's a small box, pretty much 10-centimeter cube. It's called polymerase chain reaction machine. So what we do is have a sequence for part of the genome sequence from the Corona 2 virus, and we find SNPs, single nucleotide polymorphisms, small sections of the genome that we can make DNA probes to put on the machine. And we worked with CDC. I was called in last fall to work with CDC to do some of the genome sequencing on the Corona 2 virus. And part of my research team's goal was to develop SNPs that could be used for quick identification of coronavirus from any other closely related virus, like the common flu virus, which is also a coronavirus, or the bovine coronavirus, which attacks calves on farms. There's a lot of different coronaviruses. So we developed this test with a bunch of other genomicists on the planet, and then made it available on small diagnostic devices, polymerase chain reaction. So the device that we have in Canada is the gold standard CDC test. 2 markers, very specific. And that's different from other devices that you might have heard about in the news that only have a 1 marker test and may have an error in identifying which coronavirus you have.
So let me just ask a couple questions on this. So you said you were called in last fall, so a year ago. Now, this is before we knew about the current coronavirus, COVID-19. So you were doing something for all coronaviruses, not specifically associated with COVID-19 at the time?
Oh, no, this is specific for COVID-19. So much of the world already knew about corona infections that were starting to take off in China on the mainland.
I thought we only heard about them in December at the earliest.
No, that would be hitting public news, but in the scientific community, we are already sequencing samples, blood samples, saliva samples, and looking at this virus and trying to understand, is this really a different virus? Has there been an evolution from Corona 1, which was the SARS virus? And that work started already back summer in 2019 when that sequencing started.
I heard that it came out of a market in Wuhan in December of 2019. You're saying that actually this market with bats was not in December, or was earlier, or it came from somewhere else, or what?
So there's two different questions. First off, there's infection rates in people causing flu-like symptoms. And the question is, what is this virus? It's just a Corona 1 virus. It's just the common SARS virus or a flu virus. And the other question to answer, once we decided we looked at it and discovered this actually is a different sequence, this is a different virus, is where did it come from? And that work did happen late in the year, into December and January, and actually much later before they really confirmed where it came from.
So where do you think it came from? Did it come from this bat in a market in Wuhan, China?
Yeah, I believe so. I believe it came somewhere out of there. You can follow the phylogeny or the classification of these viruses and the host where they may have come from, and that's a very plausible hypothesis. I wasn't involved in any of that work, but by reviewing the literature, I believe that that's plausible explanation. It might be competing hypotheses, but
what are the competing hypotheses?
Well, you could start to think about engineering of viruses. I actually don't. By the structure of the genetic sequences that I see, it doesn't look like a genetically modified virus, and they have distinctive telltales on them. So I don't really believe that to be true. I think this is an evolutionary selection from coronavirus in a natural situation. But those are some of the competing. It could come from a different host. But I think.
But we don't really know, is what you're saying.
No, we don't know, and there's always uncertainty in science.
We're chatting today with Dr. Steven Newmaster. He is a genomics professor at the University of Guelph. He, along with some other people, has just launched a new company called Songbird Life Sciences with a point of care rapid test for COVID-19. We're going to take a break and come back more with the professor in just a minute. Stay with us. Welcome back to the Brian Crombie Radio Hour on Saga 960. We're chatting tonight with Dr. Steven Newmaster. He is a genomics professor at the University of Guelph. He specializes in molecular diagnostic systems, and he and a group of people are working on point of care rapid tests for COVID-19. And so I thought I'd ask the professor a little bit about tests and testing and what the Songbird test is. So maybe we could start with the Songbird test. What is it that you're trying to do? You say it's a little 10 by 10 centimeter box. What is this box?
So it's a small polymerase chain reaction device that we talked about a little bit earlier. It runs in 90 minutes, a 2-marker test. And the 2-marker test is really important. 2 markers to be able to differentiate Corona 2 virus from other coronaviruses. This is important because if you use a 1-marker test, you may not differentiate it from, say, the cold virus, which have very similar symptoms. And then you have a false positive for COVID-19 because it's designed to be a COVID-19 test, and it's really the cold virus. So this test on the B-Cube, so the B-Finder, the B-Kit, uses 2 markers to have a very specific test for Corona 2 virus. That's an important distinction.
And is it a nasal swab, or is it a saliva swab, or what?
It's nasal, so it's approved for nasal and oral pharyngeal. So you have to take that swab and stick it up your nose or go to the back of the throat. However, that's the approval right now. We validated in my lab a saliva sample, which is really simple. And that saliva sample method is, all this data is being provided to Health Canada, number 1. And number 2, we're doing clinical trials right now. with COVID-infected patients doing saliva and seeing how often you actually get a positive on a positive. And we're getting great results back already for the start of it. It's going to be a much simpler test, a faster test that's linked with a different type of technology on that same machine.
Okay, and so let's talk about the test. So the state of the art is this nasal swab that you get sent away and comes back in 3 to 7 days or something like that. Can you describe what that test is?
So that test is a 2-marker test. It's on a PCR machine, polymerase chain reaction machine. That's bigger. It does the exact same thing. So I have that system in my lab as well. So I have the small one and I have the big one that's run in the clinical labs that you send your samples off to, and you get the exact same result, the exact same data. So those tests are exactly the same.
And then I understand that there are some rapid tests that are in development, some that are being used in the United States, some other ones that are being in development that are swabs from the throat, saliva swabs. Do you know what those are?
Yeah, those are saliva swabs that can take a sample, and you can run it on different types of machines. So that's just the sampling. The important thing about saliva that we had to answer is in your mouth compared to in the back of your nose, there's a lot of chemistry. Some of that chemistry is related to the food you eat, and that chemistry can impede the test. So we call it PCR inhibition. So we have to do lots of experiments from different people to say, well, are there PCR inhibitors in the saliva? And what type of chemistry do you need in the test for it to work? That's quite a bit of experiments. We've been running through these for the last 6 months, and we've come up with a design that works really well. So that's, to answer your question, one part is just in the sampling and how to deal with the chemistry in the mouth. The other part is these quick tests that are on the market use a different technology than you have in the labs, the clinical labs. It's not PCR, it's isothermal amplification, or LAMP-mediated isothermal amplification. It's fast and it's quite crude. So you can get a test in 15 minutes to a half an hour. You have a greater chance of having false negatives and positives because the test is insensitive and it's not as specific. So it may identify the wrong coronavirus. So it's a good screen. The ideal situation is to have a machine that does both. So what we just got to prove, that machine has the ability to do LAMP and PCR. So the beauty of it is you can run it, and in 26 minutes, if you get a negative, there's no virus there. If you get a positive, you just leave the machine running and it does the gold marker CDC PCR test. So it's a confirmatory test.
In a longer time period.
In a longer time period. So you go from that half an hour, 26 minutes to 90 minutes. And that's an ideal situation in point of care.
Now, there's been a lot of controversy about the tests that President Donald Trump has been taking, and supposedly he takes a rapid test on a daily basis, and then this one that came out positive was a PCR test that he took in the early morning hours Friday morning. Any idea what the rapid test was that he was taking?
Yeah, they're using the Avid system in the White House, and that's that isothermal amplification that has a higher probability of false negatives and positives. So, clearly that didn't work well. And then testing all the different staff, that didn't work well. It didn't catch it. So it's not sensitive enough. And particularly when you're taking saliva samples, the viral load may not be high enough in there. And if you have a test that's not sensitive enough, it doesn't pick it up.
So,
and that's a problem.
I was speaking to someone that said that you needed to understand two different terms, sensitivity and specificity. Can you explain what the difference is between those two?
Sure, and those are key concepts for validation of any one of these diagnostic tests. So we've spent, my lab, we spend our lives working on these and publishing validation studies. Specificity is the ability to identify a specific taxa, so in viruses, a specific strain from all the closely related strains. So Corona 2 from Corona 1 from bovine coronavirus. That's specificity. You want high specificity. How do you get it? You use more markers. So the 2-marker test is excellent for doing that. A 1-marker test, well, it's not as specific because you don't have 2 different parts of the genome to get that identification. That's specificity. Sensitivity is the ability to pick up pieces of the genome. And for viruses, it's RNA. So the ability to pick up oligos of RNA. And there are so many oligos of RNA in every microliter. So a very sensitive test will pick those up and give you a result. The danger of that is, well, maybe viral load isn't enough to infect you. The great part of that is, well, you have the virus and you have the potential to infect others. The mystery in there is how much does it take to really infect someone else? What is the risk? And we don't know that in science yet. We're trying to figure that out. There's a lot of complicating factors, including people's ability to fight off the virus. But there's got to be some viral load threshold that's in there, and we want to link it to sensitivity. So you want a sensitive test to pick it up, because an insensitive test is useless.
So can you test for viral load?
Yeah, definitely. You can. So sensitivity picks up the number of fragments of RNA in a particular microliter in a very small amount. And we can quantify that. We can use quantitative PCR, and we can look at how much is there. And we can measure it.
So in some prior interviews I've done, people have talked about this 15 minutes in a close confined environment with poor ventilation being one of the best ways to get COVID-19, one of the worst ways to be effectively. And their explanation was that it takes a while to get enough viral load to get through your immune system to get infected. Does that make sense?
Yeah, it totally makes sense. And I'm not a virologist, I'm a geneticist, but the more virus you're exposed to, the more chance you're going to be infected. So that's basic virology. What we found out about the air, so we're doing these experimental air chamber experiments at Songbird. And so the great thing about working with the engineers at Songbird and their physicists is we built chambers and we asked the question, can we actually sample the virus from the air? That's not easy. So we put the virus loads in at different densities. And these are surrogate viruses. This isn't Corona 2 virus we're spraying around, but it's in a closed chamber. So it's contained and it's safe. And we'll use a bovine coronavirus, which isn't a human health factor, at different densities. And we see sensitivity. Can we pick it up out of the air? So we have an air sampler and a filter or a condenser. And then we take that virus and we do the diagnostic test. So we've been able to do that. The interesting thing that we found out is how long the virus is picked up by small water particles and floats in the air. So we have a long chamber, 25 feet long, we blow it in, and we find that it's still suspended for long periods of time. That's a big concern. That means the virus could be moving around buildings through ventilation systems. You're one of the first to hear this, but that's a big concern that we have right now. So we're validating this research before we publish.
I was told that if you have a ventilation system that has atmosphere changes per hour that are above 10, your chance of getting COVID-19 goes down dramatically, and that regrettably a lot of schools and institutions have old HVAC systems that might have 3 to 5 atmosphere changes per hour. And 3 to 5 means that you're getting, the 20 minutes to, I guess, 12 minutes of exposure to the virus. But if you're above 10, then you're only getting 10 minutes of exposure. So does better HVAC systems help your problem?
Yeah, I would think so. So not only airflow, but obviously filtration, because HEPA filters will filter out viruses. UV treatment within the HVAC systems. So one of the things Songbird does is we put in the virus and we see how we can mitigate or get rid of the virus. So that virus load in the air. So the risk of contamination, and that could be filtration, it could be UV, it could be increased flow, decreased flow. So it settles out. It could be cleaning. There's a
and when you're testing an environment, what are you doing? You're just sticking a swab up in the air, or how are you testing to see if the virus is there?
No, there's air. So for the air, there's air samplers. So it takes a certain volume of air and into a space. It looks like a little gun, actually. So you hold it in your hand, it sucks in that air. That air goes through a filter. You can sample off the filter, or another way to do it that we came up with, which is works really well, is you do a change in temperature in the air and it condenses all the droplets into water and the viruses in the water, and then you just test the water.
I spoke with a professor at McMaster who's working on sewage systems and says you can test sewage systems for COVID-19 as well. Is that true?
That's true. And there's a number of research labs that are doing that, including McMaster, but also at our University of Guelph, we have a team that's working on that right now. There was a Dutch group that first detected COVID or Corona 2 virus in sewage systems, improperly filtered sewage systems, treated sewage systems. So that's another concern.
I think April, there was a company in Ottawa, Spartan Bioscience, that got a DNA or an RNA test approved and then pulled off the market. Do you know any of that story? What happened?
Yeah, actually I do. If you look at the instrument, it has a number of different, any of these instruments has the capability of taking so many samples into a cartridge, you put in the machine, and then you press go, and it runs. And if you just look at the design does not allow you to have control samples. So in an experiment, you need a positive and negative control. So you usually have water, and you want to have a control for the Corona 2 virus. So you know it works, and you know that it's operating normally. And you need that. If you're going to do 2 markers, you need 4 wells. The problem with that machine is it didn't have enough wells to be able to run positive and negative controls for 2 markers. So its specificity and sensitivity were low. And when you take a machine, you go through all the validation, the end validation to do is put it in clinical trials with people who are infected and see if it works. You test it on 100 patients, did you come up with 100 positives? And it came up with a failing result. That's why it was pulled. But based on design, I remember looking at design saying, well, it's not going to work. And this is why, it's improperly designed cartridges for this test. It works for other, identifying other organisms, but it's not going to work well for the Corona 2 virus unless they redesign the whole cartridge system.
Well, it's a fascinating business that you're in. We're chatting tonight with Dr. Steven Newmaster. He is a genomics professor at the University of Guelph. We're talking about point of care testing for COVID-19. We're going to take a break and come back more with the professor in just a minute. Stay with us. Welcome back to the Brian Crombie Radio Hour at Saga 960. I come to you every Monday through Friday at 6 o'clock. I bring you interviews with interesting people. You can get me on your AM dial at 960 AM, or you can get me streamed online at www.saga960am.ca, or you can get all my video casts and podcasts after the fact on my website, briancrombie.com. Tonight, we're talking point of care testing for COVID-19 with Dr. Stephen Newmaster. He's a genomics professor at the University of Guelph. He specializes in molecular diagnostic systems of plants, probiotics, and pathogens. And he's currently working with a group of people at Songbird Life Science on a COVID-19 rapid point of care test. He's recently received a research award to extend his R&D on novel pathogen detection in China. And among his many roles and accolades, he's a professor and director of the Natural Health Products Research Alliance, a chief science officer at True Idea. He's a recipient of the CEDA ICID Award for enhancing academic practice in disciplines. Sounds like a pretty impressive CV. Professor, welcome back to our show. Maybe I can ask you a question. You've got this rapid test, and it sounds like it's a critical stage in our reopening. So the question is, how do you think we implement your tests and reopen our society?
Yeah, we use it to get back to our everyday life. And the way you do that is to assess risk. What's the risk of me infecting anybody given I travel all over the place? So I'm traveling around, I'm going to meetings, and I come into a place, I go home, and I'll go and visit my parents, and they'll say, God, you could be infected. And that's a threat to everyone. And my response is, I can test. I have a test. I have it in my hand. I can test just before I come see you, just before I go into a particular area to work, before I teach, before my students come in. I can do that. So the question is, how do you make that available to everybody? So you can travel on planes, go to school, come into work. We have that available. That's the solution to getting us back into society. Let's assess the risk that I'm an infection risk to anybody around me.
And so this would be these rapid tests that you're developing. That's the solution.
Yes, and it's a genomic-based test. Now, one thing we haven't talked about is there are other tests like the antigen test. I think it's important to point out they answer different questions. The antigen test tells you, well, you've been exposed to the virus, your body has produced antibodies, and we can measure these. And that's good for you. That's good, I think, to assess employees and their ability to fight off the virus and be able to work. So pilots, you want pilots coming into your plane you'd like to know which ones have antibodies, which ones don't. Teachers. People who are running critical power supply. It's like, which of our staff already have immunity to the virus? This is good to know.
This is because they've had the virus and have therefore naturally developed immunity, or also potentially after a vaccine. Will someone
Both.
with a vaccine have the antigen?
It's the same thing, whether you get a vaccine and you're exposed, or you're exposed in the environment or from another person, you're going to have a response which is immunity. And we can measure that through the antibody test, the antigen test.
Is the antigen antibody test available in Canada today?
It was just approved today by Avid, the Avid Antigen Test. In the US, there's quite a few instruments that have been approved, and I think we'll see a lot more very quickly. And I think that's an important tool that we need to assess which of us in our society have immunity. And remember, immunity, well, maybe not everybody knows because they're not reading the scientific literature. What we've learned in the last 6 months is immunity for the Corona 2 virus is short-lived. 3 to 6 months, it looks like. And that's not surprising because the coronavirus immunity for the common flu doesn't last long. It's one of the reasons we get a flu shot every year. You know, one is it evolves, but number two is we lose immunity, and that's just a natural.
Really? So I had understood that the reason why we may lose immunity is because the COVID-19 may mutate. You're saying we just naturally lose immunity.
Yeah, there's two factors that are at play, at least two factors that are at play. Yes, that's true. So there's that one test to say, have you been exposed? Do you have immunity? And the other test is just answering the question, do you have the virus in your body? Which means you could spread it to others. And you may not have both. You may have immunity and no virus because you had the virus, a month ago.
Right.
There's no more virus in your body, but you do have the antibodies.
But what you are saying is if you think that the immunity lasts 3 to 6 months, we're going to be having to take a vaccine on a very regular basis.
Yeah, probably. And it's going to evolve. And we're already looking at part of the research grant that I have from the Chinese Academy of Medicine is to look at the infection rates in different parts of the world and see whether or not the virus is evolving.
And have you found out so far?
We haven't seen any real strong evidence for evolution rates that are very high. Not yet, but we're only going into the next flu season, and that's usually when it happens. So in theory, you would expect to see this late this year, early next year.
So you talked about having these rapid tests available for people so they could take them before they go into jobs or meet their parents or come home or teach or something like that. So is this something that you think everyone's going to buy a bunch of tests and take a test a day? Or is this going to be something that University of Guelph is going to have as available for all the employees to take as they come to work, and rather than punch a time clock, they're going to be taking a test? How's it going to work?
I think it's going to roll out in stages, and we're having these discussions with federal and provincial governments, but also with industry that's very interested in understanding what is the risk of infection. So definitely businesses will be rolling this out for their employees and making it available. And then it'll start to move closer to us in society where we have availability. Right now we can go to a clinic and wait, depending on where you are, wait times. Eventually this test is going to be available in public places, much like you would go into a pharmacy and get a blood test, check blood sugar. That's very conceivable. The molecular diagnostics of this test is advancing very quickly, and that test is going to get cheaper, faster, and more available.
So I spoke with the CEO of the Oxford University Healthcare Network from the UK, and he said he was in final validation for a saliva test that it sounded to me like almost was like a pregnancy test, that it was a strip or like a a chlorine test for your pool, that you put it in the solution and it turned a certain color depending on whether you had the COVID-19 virus or not. And he was suggesting that the economics, the costs were such that the current test, he thought, for the PCR was above $25, and this one might be less than $1. Do those two things sound right?
They do. They do sound right. These strip tests don't have high specificity, but they're a rapid test and they can be really cheap. And if they're mass produced, they could be pennies. The problem is they're not very specific, and nor are they very sensitive. So those tests, when you take it, if you did get a positive on it, you would want to go and get a confirmatory test. You would want to go and get the PCR test, which is the gold standard. There are other tests too, like a biosensor test. And a biosensor test is a different concept. We have to go back to the comments I made about probes. When you make a probe for a specific part of the genome that identifies this is Corona 2 virus, you can make it into a PCR test and validate it. We have a process for doing that. A biosensor is a different biotechnology and concept. It's the concept where you have this probe within, and it's going to be a little bit hard for me to explain, but you have it within this very, very small electronic device. And they can be a centimeter by centimeter chip with a whole pile of probes on it. You could identify a lot of different pathogens. This is what we're going to see in the future. So this is very futuristic. It's like the tricorder, and we're working on this in my lab.
It's like the tricorder from Star Trek.
You got it. Yeah, we're building the tricorder. So when you have a virus RNA pass over it and connect with the probe, and you have it on a very thin molecular material, like a carbon-based material. Graphene is a good example. It looks like a honeycomb. A charge moves through, a very minor charge, and you can use that for a signal. So that means that you no longer need reagents. There's no cost really to this. It's reusable. You could test in the air. So some of these instruments we hear about, it's like, well, you can test Corona 2 detection in the air. That's possible through a biosensor. And there's a lot of investment in biosensors. The challenge is right now is this is cutting edge science, and we need to validate it before it can be commercially available. And we have to go through that specificity and sensitivity, and we don't have a process in place for doing that. We do for PCR. We've been doing that for foodborne pathogens, but we haven't for biosensors yet. It's coming, but we don't have it yet.
And who's working on these biosensors?
There's a lot of different labs. It's not just my lab working on this. There's a lot of labs working on it. And down in Silicon Valley, I bet there's over a dozen different labs trying to produce biosensors using graphene. Graphene's in short supply, so you need a good source of graphene. That would be a really good material to build a biosensor on. We're going to hear about it very much in the future. The more money that's put into this as R&D, the sooner it happens. So it could be definitely this time next year where we have commercial biosensors that we're using. And at Songbird, we're going to have those, and we're going to be testing in air and water using biosensors. That's the path we're moving down. PCR will be the standard to test it against. So you have an orthogonal approach, 2 ways to be able to measure the same thing. And if they're exactly the same, you now have a validation method. So that's the process that we're moving.
But you think it's a year away?
Up to a year, maybe shorter. We'll see how fast it goes and how much more research dollars we get, how many more scientists I can hire to do all the experiments. There's a lot of steps.
Well, fascinating work that you're involved in. So we've got the PCR test that is the gold standard, and that's test that I presume has been around for a long period of time. We've just adapted it for COVID-19. Is that correct?
Yeah, that's correct. It's a test that's been around for, since the 70s, 80s. It's definitely a test that has kept all of our food safe from foodborne pathogens the last 20 years. Okay,
so if the PCR is the gold standard, next would be what, your 2 factor tests that you're talking about?
That is the PCR test, the two marker test. That's the gold standard.
But you're doing it in a rapid process rather than the PCR test that goes to a central lab.
Well, the central lab, it takes the same amount of time. It's just, you have to send it in the mail. It's sitting in the queue. But if it's just running in the lab, it takes the same amount of time.
So what's the difference between the PCR? What's the difference between the PCR the gold standard test and your 10 centimeter box test, just that it's something you can take to a point of care?
Yeah, we've made it smaller, and we've eliminated a few of the steps in the process of running it through. So we've made it a condensed standard operating protocol that's run on the machine.
Okay, and so that's a two-factor test, but it's still a PCR test.
Yeah.
And then you get to this Avid test, and the Avid test is what?
It's called lamp-mediated isothermal amplification. So it's a lamp test. It's one of the steps that's kind of before the PCR test.
Okay.
It identifies that there's virus there, but it's not very specific.
And that would be the same of this saliva test that I was talking about that Oxford's working on?
Yeah, it's very similar. Yeah. And the saliva test works really well with isothermal amplification.
Okay. And then the next one would be this tricorder kind of test, which is called what?
That's a biosensor.
A biosensor.
Yeah.
So is that the sort of the array of the different potential tests?
From a genetic perspective, yes. And then we have the antibody test, which is different. It's a protein-based test, chemical test.
But it's not testing if you've got the virus, it's testing if you did have the virus.
Yeah, you're a good student.
Okay. And then all these tests are sort of yes and no. They say, do you have the virus or not? Do any of them tell you how much of the virus you've got? Because so much of what I've been sort of hearing is that you need to have a large viral load, and that kids, for example, get the virus but have a good immunity system, and so therefore they get rid of it. And there's not enough viral load. And then I had one person who told me that they were concerned that some of the testing may not pick up potential infection because the viral load wasn't big enough. Well, if the viral load's not big enough, do they get the virus, get the antibodies, but never get any symptoms? So can you test viral load?
Not yet. We can't quantify yet. It's a very difficult thing to do. We're working on quantification, and the PCR machine we've been talking about can be yes, no for an answer. Virus is there, yes or no. And it can also do quantitative PCR. So it can tell you how many of these oligos of RNA are found. We haven't built those models yet. We haven't validated that yet. That would be a really, that's one of our next goals, research goals, to be able to develop that. The biosensors can measure how many of these virus oligos or virus probe events are happening. And you could quantify that through experiments and have a quantitative tool. The antibody test could quantify. It doesn't right now. So it identifies that you have antibodies. There are certain methods in the lab that you can do to quantify, but the point of care devices don't do that yet. Again, I think by next year, we're going to have some of those tools.
So these biosensor tests, are they going to be set up in like airports and we're going to walk through a biosensor before like a security magnetron before we can board a plane?
A really good way that they would work, and I've been thinking about this, is like a breathalyzer. And it's probably just going to look like a pen or a pencil, and you just blow into it, and it's going to tell you your viral load, and it's going to tell you which viruses. And it's not only going to be Corona 2 viruses, but it's going to say, oh, you have a flu virus. And maybe that's important to keep people out of certain work areas, like stay home for 2 days until your viral load's lower.
So this biosensor, will it be able to tell us you've got nothing, or you got COVID, or you got the flu, or you got the common cold?
It could do that. That's what we're working on. Multiple probes for different viruses, different pathogens.
God, you really are going to be Dr. What was his name? McCoy? Was that from Star Trek?
Yeah, that's right, from Star Trek.
Spectacular.
Yeah.
Well, we're not talking with Dr. McCoy from Star Trek. We're talking to Dr. Steven Newmaster from Guelph University. He's a genomics professor, and he's specializing in these point-of-care tests right now for COVID-19. We're going to take a break and come back with a couple of final comments in just a minute. Stay with us. Welcome back to the Brian Crombie Radio Hour. Great, interesting conversation with Dr. Steven Newmaster. He's a genomics professor at the University of Guelph. He's currently working with a team of international scientists to develop and validate a point-of-care diagnostic tool for pathogens, which would include bacteria and viruses that cause health issues for us, including COVID-19. We've talked about a new company called Songbird Health Sciences that he's just co-founded, that's launched, that's going to be trying to help us with this point of care system that's 10 centimeter by 10 centimeter two-factor test, comparable to the PCR, but something that we can, I guess, walk around with or take to our schools or take to our workplaces. And we've talked about a bunch of other potential devices and tests, including a tricorder like biosensor that the doctor's working on, that we might be able to use maybe a year from now to tell us whether we got COVID-19, whether we got the flu, whether we got the common cold, or whether we're okay to come to work or go into the sporting event or whatever it is. So fascinating. Professor, you're obviously very knowledgeable in this area. One of the big controversies in Ottawa of late has been that I guess there were a bunch of people that were part of a sort of an early warning research process, and that we got rid of them, and therefore we didn't have as good a early warning system for pandemics as maybe we should have. And then, there's some people that think that we should have been expecting a pandemic, that we had the Spanish flu 100 years ago and it was about time for this 100-year pandemic. But then other people that say, well, no, we've actually had 3 or 4 major viruses, SARS back in 2003 and Ebola and other things, and it was only a matter of time. So I guess my question is, what are we doing at the government? What should we be doing? And should we be doing something really quickly because we need to get prepared for something more?
Well, Brian, I think we're really lucky. We were hit with a virus that is a flu virus. It could have been a lot worse. And I think we got caught being complacent and not having the infrastructure in place to deal with this. And we see how the government's responding. Government didn't know how to deal with this because we haven't really taken it seriously in society. There's a basic concept that I teach in population genetics, and it seems really obvious when you start to think about it, but it's something we need to think about pretty seriously in society right now. And it's based on ecological theory. And it doesn't matter what the species is. As populations become denser, the probability of disease goes up. And it's not a straight line relationship. So this is a curved line that goes up, and we hit this point of inflection when population's going up, but the risk of disease goes up considerably. And we've seen this in the human population, and we've been lucky to deal with it through modern medicine, modern science. But there's this concept of a pandemic, a disease that we're not being able to deal with faster than it can take down the population. And there's a population correction. And you see this in all kinds of organisms that get really dense populations. You see it in agriculture where you put too many chickens into a barn and you reach that critical threshold, a disease goes through and wipes them out. And we feed them lots of antibiotics to deal with it. So this is a real theoretical concept. So we're hit with it. How do we deal with it? We need proper infrastructure. We need to have the proper medicines in place to deal with it. From our perspective, diagnosing is key. You need to know where the virus is and how it's spreading, and we didn't have that. There's a lot of news about testing, and the testing was not in place. It's coming into place now, but we were caught off guard in society.
You said that we were lucky that it was just a flu vaccine. President Trump has been sort of almost talking it down by saying, well, it's just like the flu. Is it just a flu? Is it just a flu virus?
Well, the coronavirus is a flu virus. It's a little bit different that there's a very high temperature trait that goes along with it, and a high probability of getting secondary lung infections if you're in the risk category. So if you're immune compromised or you're an older population, if there's some kind of immune compromised part of your body, you're at risk then of having a secondary infection, which could be deadly. That's a problem, and that's serious. But there are much worse viruses that could become a pandemic and kill people very quickly.
So I guess what you're saying, if I could put in my words, is that this, for a lot of people, is a flu virus, but for people that are have immunocompromised immune systems, are in vulnerable categories, the mortality is higher than the regular flu.
Correct. Yeah, that's what we understand about the flu virus. What can we do? But what do we learn from this right now? We need to have infrastructure in place to deal with it. So from my perspective, having a point of care device in the hands of industry, in society, in education, where we can pick this up and detect it quickly is really important. I think so the instrument that we were talking about today, so this high-risk B cube, one of the important points of it that we haven't talked about is it's connected to the web system. So the machine, if you do a test on it right now, if I did a saliva test from you and ran it on the machine, and I get a result and I'm not connected to the internet, the machine still ran. And as soon as it picks up a cell network or the internet, the data goes up to the cloud, and we have mathematical algorithms that analyze and say positive or negative. But we also understand about your test what that virus RNA looks like, a little bit about what that virus RNA looks like. And we also have, there's a date and a geographic location through a GPS. We know where it was, when it was, how many tests. All these machines can be connected in different swarms. This isn't something we have in society right now in our clinical labs. They're not interconnected like this. So these types of machines that are connected, and then you could have a readout somewhere and go, oh, look at how infection rates are going up in mining camps in this part of the north, or within schools. You would be able to go in and quickly deal with infection rates. And it could be for different viruses. So we need to build out this infrastructure so that we can catch this early and deal with it.
Well, Professor Dr. Steven Newmaster, genomics professor at University of Guelph, founder of Songbird Health Sciences, thank you very much for telling us about testing for COVID-19 and point of care and how it's going to change our lives, and hopefully for the better, particularly when we get not only your 10 by 10 centimeter box, but the tricorder like biosensor a year from now. Really appreciate your time, sir.
My pleasure, Brian, and thank you for keeping everyone educated. This is the way to do it.
Well, that's our show for tonight. Thanks so much for joining us. See you tomorrow. Good night.